Hello everyone. Today I will be presenting our work on fuzz testing to detect platform-dependent divergence for heterogeneous applications. My name is Qian. I'm a postdoc working with Professor Kim at UCLA. The emerging data and compute-intensive software applications are increasingly constructed to leverage heterogeneous architectures. A heterogeneous application refers to the software application that consists of both host code and kernel code and can offload these compute-intensive kernels from CPU to FPGA for acceleration. Such architecture is becoming widely available to the industry, such as AWS EC2 F1 instances. There has been high-level synthesis that raises the programming abstraction level to C programming languages. However, testing such heterogeneous applications with high-level synthesis, especially for FPGAs, has been a long pain. This is because these applications may look similar to regular C code, but they include hardware synthesis details in terms of pragmas and directives. Therefore, their execution behavior under heterogeneous architectures may diverge significantly from CPU, and we call it as a platform-dependent divergence. In fact, we did a simple search on the Xilinx forum, which is similar to the Stack Overflow, but specifically for software developers in this domain. These real-world posts from Xilinx forum reflect the developers' desire to test this platform-dependent divergence. Such divergence may come from various sources. Hardware accelerators use custom bitwidth internally, while they communicate with CPU using primitive types. Overflows show up much more frequently in accelerators, and it is difficult to predict the consequent impacts. Another important source is linking memory management on FPGA. Each memory access, even for the re-access with an out-of-bound index, will be mapped to the physical address. This could change the code logic or produce the wrong result silently. Additionally, different functions run parallelly on hardware, even for the simulation. This may include execution paths that can never be activated by C software testing. Fuzzing is highly effective. It starts from the seed inputs, runs a program on the selected input, generates new input by mutating the previous input, and adds new input to the queue if they improve the given guidance metric, such as branch coverage. However, traditional fuzzing is for CPU applications only and doesn't account for the platform details. Here we propose HeteroFuzz to detect platform-dependent divergence errors in heterogeneous applications with FPGAs. In this domain, fuzzing has its own limitations. First, branch coverage cannot be derived directly from the synthesized kernel. This is because the branching logic is implemented using multiplexers at the hardware level. Each branch in the synthesized kernel code is executed or simulated in parallel as long as the previous signals are ready. That being said, all of the branches are activated. However, the output from the untaken branch is never used. Next, mutations are ineffective to yield divergence-inducing inputs. More importantly, the high-level synthesis compilation and simulation time takes minutes. Such long latency prohibits the efficiency of fuzzing. We reinvent fuzz testing for the heterogeneous applications with novel techniques specifically designed to address these three challenges. We collect feedback from both the host code on CPU execution and the kernel code on FPGA simulation. During fuzzing, we prioritize the mutation operations that lead to divergent symptoms across platforms, and we expedite the fuzzing process by early terminating some of the simulation attempts based on analyzing the input range. Our observation is that platform-dependent behavior can be exposed by monitoring accelerator-relevant spectra. Here, the term spectra means some contiguous ranges for the variables, loop executions, or array accesses. To collect accelerator feedback from the kernel simulation, we analyze the inserted high-level synthesis pragmas on directives, map them to their associated FPGA-relevant spectra, and monitor the simulation process for the specific types of feedback. This table summarizes our 5 kinds of feedback. For example, we have a kernel code doing the accumulation over the given array. We scan this code and find the 4 inserted pragmas and directives, including custom bit width, maximum array size, and loop unrolling. Consequently, the accelerator feedback for this program is automatically defined as the value range of the variables associated with custom bit width, the set of accessed array offset, and the actual number of loop iterations. Collecting these values doesn't incur additional hardware-level instrumentation, as such information can be extracted from HeteroFuzz simulation results. Then during fuzzing, any inputs that advance either host branches or accelerator feedback will be saved for further mutations. Mutations in fuzz testing represent input modifications to explore the input space. Different from the mutations used in traditional fuzzing like AFL, which assumes a uniform distribution for all of the mutation operations. We perform probabilistic mutations to prioritize some of the mutations over the others. Our insight is that different mutations contribute to application-specific platform divergence in different degrees. HeteroFuzz uses 6 kinds of mutations for arrays and matrices because accelerators are designed to batch process multiple elements in parallel. We assign different activation probabilities to individual mutations and update their probabilities based on accelerator feedback. For example, if a new child input generated by mutation M3 increases the monitored feedback, M3 will have a higher activation probability in the next input mutation. To reduce the long latency of repetitive hardware simulation, HeteroFuzz memorizes a range of scene kernel input values. We use a global variable to indicate whether the hardware simulation should be invoked or not. This variable is set to true if the range or the data size of a scene kernel inputs grow beyond the current records. Our observation is that in FPGA, a variable is mapped to the contiguous range of values. FPGA execution with inputs that fit in the memorized range can either be fully correct or only report a redundant divergence symptom arising from trying out a new value exceeding the safe range. Thus, we can safely obviate such executions to speed up the input generation process. We evaluate HeteroFuzz in both the divergence detection capability and the speedup. As no existing fuzzing is applicable for heterogeneous applications, we construct 3 downgraded versions as baselines to evaluate 3 optimizations in isolation. Each baseline retains 1 optimization without the others. First, multi-divergence feedback enables the divergence detection capability of HeteroFuzz. Overall, 57% of our generated inputs are divergence-inducing inputs. Compared to WithoutSpectra, we find 7.7 times divergence-inducing inputs, which detect 3.7 times divergence symptoms. Probabilistic mutations improve the chance of generating divergence-inducing inputs, and thus expedites the symptom detection process. Compared to without mutation, HeteroFuzz achieves 17.5 times speedup in detecting the same set of divergence errors. By reducing the unnecessary hardware simulation costs, HeteroFuzz speeds up the testing process by 8.8 times without sacrificing the error detection capability. To sum up, we propose HeteroFuzz to adapt fuzzing to heterogeneous applications with a long latency. It combines time monitoring of branch coverage and accelerator feedback, probabilistic mutations with dynamic activation probabilities, selective invocation that obviate the redundant simulations. Thank you.